I've made this video to help you with your written answers for question 1 part B of the written assessment for LV02.1K. I'll show you the question in a moment, but before we do that I just wanted to run through what primary and secondary balance are. And we're talking about balancing the inertia forces that a piston is subject to. So we need, as I say, a revision of primary and secondary balance. Now, primary balance is fairly easy to get your head around. In this image here, we can see that I've got two pistons moving upwards and two pistons moving downwards. So the inertia forces that each of those pistons is subjected to are balanced by the pistons moving in the opposite direction. So there would be an inertia force on the pistons moving upwards, which is counteracted by the inertia force of the pistons moving downwards. So theoretically, they balance each other. That's called primary balance. Now the problem is that, believe it or not, the pistons moving upwards move at a very slightly different speed, or they accelerate at a slightly different rate to the pistons moving downwards. I'm going to show you this image here. So it's a diagram of a piston moving up and down and rotating the crankshaft. I'm just going to freeze this diagram for a moment. And when I've frozen it, you can see that there is a triangle shaped formed between the gudgeon pin, which attaches the piston to the connecting rod, the main journal of the crankshaft, and the big end journal of the crankshaft. So these 3 points, gudgeon pin, main journal, big end journal, form a triangle. And that triangle is continuously changing shape. Just run the video again and you can see that the shape of that triangle is continuously changing. Now what that means is that the piston will move at a different rate on the first half of its travel upwards compared to the second half of travel, and vice versa. When it comes down, it will move a certain rate on the first half of travel and then a different rate on the second half of travel. Okay, so what that means is when we've got one piston moving upwards and one piston moving downwards, or in a 4-cylinder, two pistons moving upwards and two pistons moving downwards, they will be moving at slightly different rates. They will start their journey at the same time and finish their journey at the same time, but during the journey from top to bottom and from bottom to top, they will move at slightly different rates. Now, force is equal to mass times acceleration. So if we assume that all four masses of these pistons are equal, then that shouldn't make any difference. But we've just said that because of the shape of the triangle formed, that they will accelerate downwards and upwards at very, very slightly different rates. So that means that the force, the inertia force, that each piston is subjected to will be very slightly different. So even though we have two pistons moving down and two pistons moving up, the fact that they are moving at slightly different rates means that we do not have secondary balance, because the inertia forces aren't exactly equal. So this engine here has primary balance, but it doesn't have secondary balance. So here is the actual question, part B of question 1. State one advantage and one disadvantage of each engine type configuration. And the first one is an inline engine. That's what we've been talking about here. Here's a diagram of an inline engine, 4-cylinder inline engine. Now we already know that that has primary balance because two pistons are moving up and two pistons are moving down, so the two sets of forces counteract each other. But we know that the pistons moving up aren't accelerating at the same rate as the pistons moving down, so it doesn't have secondary balance. It's not perfectly balanced, in other words. Another disadvantage is that there is a limit to how many pistons can be positioned in line.
So what Cadence is showing here is that the shaft, when it's long, is able to twist. Go, give it a twist for us, Cadence. Right, yeah, so there's lots of torsional reaction to that shaft. I'm just going to stop it there and then we'll shorten. Okay, well done, Cadence. What we've done is we've reduced the length of the shaft, the broom shaft in the vise. Go ahead, Cadence, give it a twist. And so, Cadence, is that more difficult to twist?
Yeah.
Excellent, well done, Cadence, thank you.
So what that video of Cadence in the workshop was trying to show you was that if you have a really long crankshaft, you're going to have more twisting of the crankshaft, so more torsional vibration of the crankshaft. And generally, I would say the maximum number of pistons is 6. So we've got a 1, 2, 3, 4, 5, 6 cylinder engine here. I did have a look on the internet and I found an example. It's a really old-fashioned engine because it's actually got side valves, but this is an 8-cylinder engine from a Packard, which was an American car way back. Realistically though, nowadays the maximum that you're going to see is 6 cylinders on an inline engine because, as I say, if you go longer than that, you're going to have too much torsional vibration or distortion of your crankshaft. So now we are aware that there is a limit to how long our crankshaft can be and therefore how many pistons we can have positioned on it in an inline engine. Realistically, the maximum is going to be 6. Let's go back and have a look at the other types of engine that we need to be familiar with. So we've covered the inline engine. We need to have a look at a V setup and an opposed setup. So this next slide has some images of the 3 types. An inline, a V, and over here, both of these actually are horizontally opposed engines. So we're aware of the advantages and disadvantages of an inline. With a V engine, the advantage is that we can get a lot more pistons, so therefore a larger engine capacity on a relatively short crankshaft. Alright, so there's our crankshaft. So that engine is very compact. We can fit a very high capacity engine into a relatively small space. Definitely an advantage. It has primary balance, so for every piston that's moving upwards, there is a piston moving in the opposite direction. So it has primary balance, but again, this one wouldn't have secondary balance because the pistons will be moving at slightly different speeds. Another disadvantage is that we've got 2 cylinder heads required with 2 valve trains, 2 camshafts, so it makes the engine much more complex, more expensive to manufacture. This one over here is our opposed engine, and the beauty of this is that it has both primary and secondary balance. This is perfectly balanced, very, very smooth operation. The disadvantage of this one again is that we've got 2 of everything, 2 cylinder heads, 2 camshafts, 2 drivetrain gears, so it's very complicated and therefore expensive to manufacture. One of the other major advantages is that being flat instead of vertical, so in other words horizontal, means we can mount the engine in a more aerodynamic bodywork, and the weight of the engine components are all much lower down, closer to the actual chassis, so it lowers the centre of gravity, which improves the road holding of the car as it's being driven. So yeah, lots of advantages for this one. But the major disadvantage is that it's complicated and very expensive to manufacture. Okay, hope that helps.